Hello there. For this week's experiment, we will be looking at synthesis of stilbene dibromide from Stilbene. This is supposed to be a continuation from our previous experiment on synthesis of stilbene from benzaldehyde, and the idea is to use that product to synthesize the stilbene dibromide. Uh, the purpose of synthesizing stilbene dibromide is because the product itself is a precursor for another organic compound called diphenyl acetylene. Whereas this diphenyl acetylene is also an important reagent for the synthesis of hexaphenyl benzene. And as you can see, the stilbene dibromide, before it converts to the diphenyl acetylene, it comes from benzaldehyde reacting with a Witting reagent, as we saw last week, and the stilbene then undergo addition reaction with a bromine molecule to give us a dibromostilbene. Then further elimination reaction of the dibromostilbene gives the diphenyl acetylene. On the other hand, benzaldehyde reaction can give us benzoin, and further oxidation of benzoin gives us benzyl. And when this benzyl reacts with 1,3 diphenyl acetone, then we will have the tetraphenyl cyclopentadiene. The final reaction in this long mechanism is when this tetraphenyl cyclopentadienone reacts with diphenyl acetylene, it gives us hexaphenyl benzene. So it's just all about providing an input to the whole mechanism that you can see here. And so the contribution we would like to make for this whole reaction is by providing a dibromostilbene, and we can synthesize dibromostilbene from stilbene by adding a bromine molecule. So the way the bromine adds is that two bromine molecule will add into the double bond to saturate the double bond, and then you will have a saturated double bond with two bromines in it. However, there is one problem here. We can use bromine molecule, but bromine molecule is fatal and toxic, especially if inhaled. Even it is also toxic to the skin if it comes in contact, and can cause severe burns too. So instead of bromine, the pyridinium hydrobromide perbromide is going to substitute that reagent, and this is a common practice in most organic chemistry experiments, that not only a toxic reagent, there are also times we can look for alternative reagents, either because we do not have the required reagent in the lab, or we just want to make it more efficient in terms of cost, or in terms of safety, or in terms of environmental friendly product, to produce environmental friendly product. But that doesn't mean here that this solid compound, the pyridinium hydrobromide perbromide, is not a hazardous substance. In fact, it is a hazardous substance, and the only advantage is bromine is liquid, and it just have a more danger than this reagent we are using, which is solid, and that's why we have to make that a good choice. And again, one thing to mention here before you use the pyridinium hydrobromide per bromide, that compound is moisture sensitive, very much moisture sensitive, and it can absorb lots of moisture if it gets contact into air. I mean, such reactions are supposed to be done in a glove box, but for this experiment we may not do it in a glove box, but you can prevent by taking the amount of sample you need from the bottle very quick, and then do the reaction, then just let it stay with the cap open. So where does the bromide, the dibromine come from? It is from the pyridinium hydrobromide per bromide, that it undergoes an electro, you know, it goes through through a charge separation, and in that case it makes the bromine molecule available by just switching and by departing one of the bromine into the electrophilic nitrogen, and the other molecule will come out, the other two bromines will come out as a dibromide, which will be ready for the electrophilic addition into the Stilbene double bond. So in the actual mechanism, the double bond attacks the bromine molecule, and one of the bromine departs. And what happens is, because this is an addition reaction, and in addition reaction we have two major intermediates that result three kinds of products. The mechanism you see with the cyclic bromine is called a cyclic halogenate ion intermediate, which the cycle have to be formed with a three-member cycle have to be formed with the halogen part of the cycle. And what's unique about this intermediate is that so the other bromine can attack it from only one side, which we call it syn addition, and in either way, when it attacks it from one side to the right side or to the left side, in both cases we will have a trans product. The other intermediate for in addition reaction is the ion pair intermediate, and in this ion pair one of the bromine have to be attached and the other have to float in the air or in the reaction vessel, and depending also on the substance R groups around the double bond, that other bromine can attack from the bottom where there is the other bromide, or from the top opposite to the bromine available there. And in the first case it gives us a cis product. In the second case it gives us a trans product. So this is the same way of saying the mechanism I was explaining in the previous slide. It's just that you can see the pink and the red arrows are possibilities for this bromine to attack the carbons that had the double bond, and in either way you will have a trans product. One important chemistry here is that, if you remember last time when we synthesized stilbene from benzaldehyde, the products were isomers. Because of that, if you use a sample of stilbene, then there is an equal chance that either of these stereoisomers can react with a given reagent to produce other stereoisomers. In this case, the E will produce a methyl compound, whereas the Z isomer, the Zusammen isomer, will give you a pair of enantiomers. Well, in the actual experiment, we'll be using acetic acid, about 40 ml, and then we will be using 2 grams of stilbene and then 4 grams of pyridinium hydrobromide per bromide. And then you can heat this, make sure in a hot plate. Better to use Erlenmeyer flasks than a beaker to just be safe. And then after the reaction carries on for some time, you can cool it in ice baths so that you will collect crystals. And of course, you need to do a cold filtration in a vacuum, and you can put the solution with the crystals on a Buchner funnel, attach on the Buchner funnel, attach it to the mouth of a suction Erlenmeyer flask, and then you can do the filtration. Here it's also recommended that you use the Buchner funnel because if you try to wash the crystals using the normal funnel, they may get washed out because the water will densely wash around the tip, okay, around the mouth of the funnel. Also, good thing to remember, it's sometimes hard to sustain crystals, and just cooling the product immediately after the reaction is one good step you can follow here. But also, when you use the washing solvent, try to use an ice cold water along with methanol solution. Why is that? Because if our solvents are a little bit hot, they may dissolve the crystals, and we may lose our product. Also, whenever you use the washing, try to not pour too much solvent into the crystals so that they will not get dissolved. A thin layer chromatography will be used to show you if we have synthesized the compound purely, and we'll do the TLC chromatography for you under hexane as a mobile phase. Melting point, as you know, is one of the important techniques which we use it in organic chemistry laboratories to check the purity of a solid compound. However, the melting point of dibromide is very higher. It's more than 230. So that might not be suitable to do the melting point with the melting point equipment we have in the lab. So we can keep this aside. Recrystallization, again, as you may remember from your previous organic chemistry laboratories, this technique is used to, again, to purify a contaminated solid compound. But the problem here is that because our starting material is a mixture of two enantiomers, and the products will also be a mixture of several stereoisomers, which means the crystallization may not help us effectively as it does in a single chemical crystal to just purify the solid substance we got here as a product. Safety issues for this lab, please remember to just understand that the chemicals we're using in this experiment are dangerous. In fact, not only in this experiment, in most organic chemistry experiments, they are volatile, toxic, or hazardous, any of those, with any of those properties that we have in the lab. So, for instance, the bromine source compound we are using here is extremely hazardous, and it can cause a very serious chemical burns unless you take care from getting in contact with the chemical. It can also lead to respiratory and nasal irritation. In the same way, the glacial acetic acid has similar safety treats, so they must be handled with a great care. Again, in the lab, because we use alcohols as sanitizers most of the time, or to just we use alcohol normally to release certain glasswares and certain glasswares and equipments. But methanol is a little bit different from the other alcohols, as it is toxic, especially when it is ingested, and it can also cause blindness. So take care of in handling methanol, but also not only ingestion, you should also be very careful to not have this solvent come in contact with your skin. Because we are heating our reaction here, so most of the time, heat burners does not come from fire. Heat burners usually come from most of the time come from holding a glassware that's being heating. Why? Because it doesn't show any smoke. It doesn't put any smell most of the time, and especially some students may forgot that the glassware is being heating, or even they want to check how hot it is, and and then later they find it very hot, because it's just a glass, and it's hard to tell how hot it is unless you touch it. But please Don't do that in the lab. Instead, you can use a tongue. It's like a scissor kind of piece of instrument we use in the lab to hold flasks. But better way, even not only to transfer the glassware, but also to keep it tightly seated in the heating source. You can use the clamp that you're seeing in the slide, and you can then attach the clamp to iron stand. As you may know, spectroscopic techniques are very powerful instruments to use in organic chemistry because they give us important information about the structure. In this experiment, we'll also use IR and NMR to characterize the dibromide3. During using IR, try to use very small sample because IR samples are not recoverable, especially for the IR we will be using. But we do not have that kind of problem when we use an MR. You can just get back your sample and dry the solvent off, and then you can have your sample back. This is a continuous experiment, and please remember to save your product in the proper shelf, which will be assigned to you by the TA. And that's all for this lab lecture. If you have any question, you can email me, or you can put it as a comment in the YouTube channel, which you will find this video lecture.